Bienal that I hope you enjoyed. I'm Jon Herrera, one of the organizers and professor here at the University of the Basque Country. And for me, it's a great pleasure to introduce you to Javier Aizpurua, who is one of the top local researchers here. So he was born actually here in San Sebastian. He studied physics in Zaragoza, while he was developing a good basketball player career as well. But luckily for us, he chose to continue his career as a researcher in physics and not in basketball. Probably it's more competitive than our field, maybe, right? So he did his PhD here under the supervision of Pedro Miguel Echenique. And then he was abroad in Chalmers in Sweden, in NIST in the USA. And then later, in 2008, I think he came back here to form his own group on the field of the theory of nanophotonics, and he's been very, very successful. So he's been of the top researchers in the field worldwide, and he received the award of Euskadi Prize of Science like a couple of years ago. So this is the highest scientific recognition here in the Basque Country. He's been also one of these highly cited researchers of Elsevier, which became very famous, but I think he didn't change his affiliation to Saudi Arabia. And right now, so he's the leader of the strategy of the Basque government on quantum technologies. There is a big investment on that and a new strategy that is being developed, and he's now the leader of that strategy. So, Javi, the floor is yours.
Thank you very much, Jon, for this kind introduction. And thank you, everybody, for being here. Thank you, Genaro Isasola, as well, and Idoia García-Gurtubay, for having me here. It's really a pleasure to address you in this final talk of the Bienal, which has been very successful. Congratulations. And this is what I'm going to talk to you today about. It's addressing light matter interaction at the nanoscale. And before I run out of time, I want to acknowledge the group, which is composed of a good bunch of people. I want to acknowledge particularly Ruben Esteban, and for what I will talk today, Javier Arrieta and Adrián Delgado, connected with STM-induced microscopy and optomechanical interactions. Also, collaborations with key people, both in theory and in experiments. We have actually former members of the group, Yuan Zhang, now in China with permanent positions, Thomas Newman, now in the Czech Republic with a permanent position, and Nikolai Schmidt in Macquarie. And I will show also a lot of things developed by them in the last 6-10 years. And then other collaborations in theory with Francisco García Vidal of Universidad Autónoma, Daniel Sánchez Portal, also a local here, which is really a pleasure to work with, and two experimental groups, which I'll show a lot of results, Shen Chaodong and Guillaume Schul in China and in Strasbourg. Okay, so all these people have participated in many of the things I will show you today. What I'm going to talk about is about optical nanocavities and how optical nanocavities help us to improve the spectroscopy of matter excitations, either electronic excitations, vibrational excitations, and how this can help us to achieve intramolecular resolution and get a special regimes of optomechanics. So let's start. We want to address spectroscopy and use light to probe matter in an effective way. And when we say to probe matter, we mean to check electronic excitations, to check vibrational excitations, and we typically do that, for instance, in molecules through molecular spectroscopy, when we can send infrared light directly to get absorption, infrared absorption, or visible light to get fluorescence, which involves electronic states, or even Raman, with participation of vibrational states, which allow to identify vibrational fingerprints. The problem of going with your light probe directly on small amounts of molecules and try to get signal is that the cross sections of these processes are relatively low, and you will get most of the times noise if you go even all the way to single molecule, for instance, or single emitter. So in this context, people have used for many years optical cavities. Why people use optical cavities to enhance or improve molecular spectroscopy? Basically, the Fabry-Perot, which is the canonical cavity, you put your matter there. When you use this kind of cavity, what you achieve is basically two things. Rather than coming with light, a spread, passing once and proving this small optical cross-section, by putting the cavity, you achieve mainly to work on two magnitudes of light. What we call to make a more dense electromagnetic energy density. This is expressed through the effective Mach volume. So we trap in this cavity light. So we put more amount of electromagnetic energy in this little spot where matter is. We characterize this through a volume, effective Mach volume. So smaller volumes will mean more interaction with matter. And the other magnitude is the quality factor. Obviously, you know that when you put a Fabry-Perot, light bounces forward and back a number of times, which is given by the quality factor. These kind of cavities have millions of quality factors. So after several millions of bouncing both forth and back, the photon will escape. And obviously, instead of interacting once with the matter, if you go forth and back 1 million times, then you interact 1 million times more than with matter. So with these two magnitudes, the effective Mach volume and the quality factor, you improve your spectroscopy of whatever you put here. And actually, this even for an emitter is addressed through the Purcell factor. The decay of an emitter, an excited state in an emitter that decays, can be actually accelerated by the presence of the cavity. We call this the Purcell effect or Purcell factor. This Purcell factor is proportional exactly to the quality factor and inversely proportional to the effective Mach volume. So what we try in cavities is to reduce the effective Mach volume and to improve, to make larger the quality factor, because then you improve the effects of acceleration or intensity signal, etc. So people have tried to play with effective Mach volume and try to reduce these Fabry-Perot cavities, which are relatively big, by using microelectric resonators or photonic crystals. It takes a little bit of time to go there. Yeah, photonic crystals, which takes to the limit of diffraction limit. But all these cavities rely on the properties of light on reflective and refractive optics, right? What I want to bring today is another type of cavity whose principle of working is completely different. It's a metal, insulator metal, or even a single metal. And thanks to the electron gas of the metals, light can couple through the geometry and bring in energy and momentum to these nearby boundaries of the particle. We can put our matter here and reduce extremely the effective Mach volumes. So this is going to achieve to beat diffraction limit compared to the other cavities. But obviously, the price to pay is that being the achievement of this localization of light in a reduced effective Mach volumes, thanks to the electron gas building up the electromagnetic field, this is very frictionful, and you have very low quality factors. These metallic nanocavities have quality factors of 5 or 6. So you can trap your photons here for 5 or 6 optical cycles, and after that, they get absorbed, most of the times in the form of heat, okay? But nevertheless, because the effective Mach volume is so reduced, this can be very interesting, and it can compensate the losses and maybe do some nice numbers for the Purcell factor and the interaction improvement, okay? This is how it works for a single metallic particle. We call to this plasma excitation of the collective electron gas plasmon, right? And if you come with a light polarized like this to one of these particles, this would be the plasmon, the electromagnetic field associated to this plasmon. This is what now we call cavity. Some years ago, we used to call it nano antenna because it traps light. So depending on the decade, we use a different name. It's all the same, okay? Nanoparticle, nanoantenna, now it's nanocavity or nanoresonator. It's still the same effect, trapping light to really reduce effective Mach volume when you want to put your matter and do enhance and improve a spectroscopy of that matter, okay? So with that, we can put our matter in these plasmonic cavities or resonators and do plasmon or cavity photon exciton coupling, and we call this surface enhanced fluorescence, for instance. And now we change again the name. Now before it was antenna enhanced, cavity enhanced, but because of historical reasons, we typically call this surface enhanced. This is the metallic surface what was supposed to do the effect. But now we know that it's not just the surface, it's these plasmons and optical resonances in the metal boundaries which are responsible for the enhancement. So here where we use surface enhanced, whatever spectroscopy, we can change surface by plasmon enhanced, nanoantenna enhanced, nanocavity enhanced, etc. It's all the same. Don't get confused. I told my students all this very emphasized because you see in the literature so many names, and actually depends on the time. It's more fancy one or the other, but it means exactly the same, okay? The same we can do with infrared, Raman, absorption, and we just put surface enhanced. It can be cavity enhanced or nanoantenna enhanced, okay? And actually the interesting thing is that with these cavities, we reduce, as I say, the effective mode volume. And for this type of interactions, both the plasmon exciton or the plasmon vibration, the kind of interaction that we call G, interaction strength or interaction rate, scales, in this case with the exciton, with the inverse of the square root of the effective mode volume, in the optomechanical, in the plasmon vibration coupling, directly with the inverse of the effective mode volume. So this is giving you a hint that reducing the effective mode volume is really improving and enhancing the interactions of the photon, of the cavity photons and whatever excitation it is. Let's focus on the plasmon or cavity photon exciton coupling. A way to address this G, this coupling strength between the local field of this plasmonic resonator or nanocavity resonator with losses kappa, which is the inverse of the quality factor. So this is very large in plasmonic cavities. And then we put an exciton here, a molecular two-level system, excited state, ground state, and this can be driven, characterized by its dipolar moment, and with a decay, intrinsic decay, gamma. So we know that the coupling between these two entities, the plasmon, the cavity photons, and the dipolar moment of the two-level system can be described as G. It's a standard way to describe it. It's an energy interaction rate or energy, coupling strength, is the local field of this cavity, which is enhanced and trapped with very reduced effective mode volume, acting on the dipole. So this local field acting on the dipole, the scalar product of that, and I mean the scalar product of that, right? It's the direction of the vectors matters, gives you the oscillator strength or the coupling interaction strength, okay? So we can distinguish according to this coupling strength and how fast these two entities decay, two different regimes of interaction. And this is part of the introduction for understanding later what's coming. If the coupling strength is smaller than the losses of both the cavity and the exciton, in other words, if the interaction does not have time to really interact before some of the entities has decay, we are talking about weak coupling. Okay? In that case, you have the energy of your optical mode, your plasmon mode, you have the energy of your exciton, and the interaction between them is weak, and it only affects a kind of interference, the imaginary part of the decay. So it's just the decay rate what is affected, not the energy of the entities. But on the other hand, if we have the coupling strength very intense, very highly energetic, very fast, the exciton and the cavity photon start talking very fast before they decay, and they can construct hybridized solutions, which are not anymore the optical mode or plasmon mode and the exciton mode, but new solutions that we call lower polariton and upper polariton. We call them polaritonic or hybrid solutions, right? In these two situations, weak and strong coupling, this is in terms of the energetics. In terms of the time evolution, here in weak coupling, what we would have is what I just said before, parcel effect. One of the decays, the exciton, will be accelerated by the effect of the optical mode, and this would be the parcel effect. In a strong coupling, we would have a dynamics between the upper and lower polariton in terms of Rabi oscillations. So to summarize what I just said, in emission spectrum of an emitter in a plasmonic cavity, the presence of the cavity in the weak coupling regime would broaden the spectrum. In time domain, this would mean to accelerate the decay, and this would be weak coupling regime. Okay? So you cannot say that you have parcel effect and at the same time a strong coupling. That's contradictory. You cannot have parcel effect and strong coupling. Parcel effect is weak coupling. This is parcel effect, acceleration of the decay, broadening of the emission. and it's weak coupling. And then you can have a strong coupling with polaritonic branches, as I said, opening, and then in the spectrum you will see this as a split of energy. And in time domain, you would see not just a simple exponential decay, but a Rabi oscillations decay. And these are the time and energy fingerprints of weak and coupling regime in nanophotonics particularly, right? Well, this has been taken to nanophotonics in a plasmonic cavity. This is a special plasmonic cavity that I will talk about later again. It's a tip, a silver tip on a silver metal surface with an emitter here, a zinc phthalocyanide. And you can move your plasmonic cavity because the tip you can move transversely here on top of the emitter, more in the middle, or very far. When it's very far, you just have the plasmonic cavity emission. Okay, this is the emission of this plasmonic cavity. You excite with the bias, and then the excitation of the plasmon here emits, and this is a very bad quality factor plasmonic cavity. When you put yourself on top of the emitter, then you see this emitter emission. This is a little bit broadened now by the Purcell factor, right? But this is the excitonic emission. But you put it in between with the emitter and the plasmon interacting, then here you have this interference, very clear fingerprint of weak coupling with a Fano profile, which is the interference of the broadband cavity plasmon feature and the narrow excitonic thing. This is a fingerprint of weak coupling regime in nanophotonics, for instance. But you can go farther and try to improve the interaction. In Chris G and the group of Jeremy Baumberg reported this cucurbituryl linkage in an organic molecule, and then in this kind of plasmonic cavity, they managed to identify this split of the strong coupling regime, almost at the single molecule level. Okay, so this is a spectral fingerprint of strong coupling. And why is it interesting, a strong coupling? Well, a strong coupling in photonics and playing with these polaritonic branches means that you can play with the molecular levels, for instance. Playing with the molecular levels by just putting your two-level system in a cavity allows you to do, for instance, energy transfer in a different way, more effective maybe. It allows to do molecular spectroscopy. This kind of a strong coupling is not only between plasmon and excitons. It can be between some other resonator and another dipolar excitation. For instance, a phononic resonator in the infrared. This we do with Rainer Hillenbrand here in Nanogune. They build these infrared resonators here, boron nitride ribbons. So these are the phononic resonators. They put molecules, dipolar molecules that resonate with vibrations, and we managed to identify this fingerprint beginning of a strong coupling in the infrared regime. So you can change the spectroscopy features. You can change and modify chemical reactivity, the famous experiment by Thomas Evesen that seems to indicate some kind of change of reactivity. The role of the polaritonics is not clear yet, and many people are working on describing this interaction in the cavity much better. Okay? And since then, when it comes to govern the single emitter statistics, emission, Purcell effect in plasmonics cavity, there has been a blow-up of activity in the community of nanophotonics and plasmonics using a variety of cavities, rods, dimers, tips to control and enhance the decay of these emitters for obvious interests, single photon emission, entangled photon emission. So in the sense of quantum optics, this is promising. Drawback, these plasmonic cavities are again very lossy. Okay, so very much they get the energy from the photons and they get into heat. You have to deal and engineer that. I'm going to show you a way to engineer that. In this context of plasmonic cavities and nanocavities playing with the condensed matter excitation, electronic excitations, vibration excitations, what I want to bring to you or to your attention today is a type of extreme nanocavities, plasmonic nanocavities. And it's this type of two cavities I want you to understand today. One is more top-down, it's a scanning-proof microscopy. It's a natural plasmonic cavity. It's a metallic tip on a metallic substrate, and we're going to be able to control with all the capabilities of scanning-proof microscopies, identify and find one single emitter, put ourselves on top of it, and play with it. Retract the tip, decrease the field, increase the field, try to scan it, etc. This is a very top-down, STM, ultra-high vacuum, low temperature. This is a very academic environment. For physicists, this is paradise, because everything is very under control here. The position of the meter, the local fields, very low temperature, high vacuum. On the other hand, you have the other approach, more bottom-up from wet chemistry. You have the metal surface. You deposit your matter, a self-assembled monolayer, for instance, of molecules here, and you deposit another particle on top, a gold nanoparticle. So you build a gold nanoparticle, gold film sandwich structure where we're going to prove this self-assembly monolayer. This is typically done with wet chemistry methods at room temperature, and it's more dirty, so to say. So some chemist told me a long time ago, don't call it dirty, call it more realistic. But this is probably what you can take and portable, more easy, and there is a big effort to try to play with these emitters here and do kind of quantum optics of a few emitters here at room temperature. Because obviously here you can do things better, but it's much harder to transport a high vacuum chamber, right? So how are we going to use these special cavities, extreme cavities, to do special things with emitters? The first thing I want to show you is one of these scan-improved microscopies achieving intramolecular resolution in light emission. This is fascinating. It's this kind of situation that I just described. Let me just focus a little bit more on it. It's the tip on a metal. We put an emitter in the middle. We apply a bias, which is a source of energy. So we are going to have the energy enough to decay into photons. And actually, photons come out from the situation, bringing information of the emitter. But sometimes you can not rely only on the bias. You can also put laser in, photon in, and get photon out to do Raman or photoluminescence. So there is electroluminescence or photoluminescence, depending on the source of excitation. How we address this theoretically? How are we going to understand both the light emission and the features of the tip when we scan and so on? If you go to a very simple description, on top of what I just described, which is the Purcell factor, which is the acceleration of the emission, of the total decay, is connected with this coupling strength to the square, by the way. And this coupling strength is what I just described, the local field acting on the point dipole. So if we have a molecule, a two-level emitter, with a point dipole localized like this, a local field acting on that, this will be the coupling. Okay, local field acting on the point dipole. But we need more than that for light emission. A parallel and complementary way to describe light emission is this emission rate of this single emitter, this dipole, two-level system, which is composed of two terms. One is the excitation rate here, and this excitation rate is basically the local field. This is the plasmonic enhancement. It's this field to the square. So you come with light, and you excite to the square the field enhancement. But you are going to excite more the dipole. But the other term here, if you can see it here in blue, is what we call the radiative yield or the quantum efficiency. There are different names, but it means all the same. It means once you excite your dipole, your two-level system, how much of the decay of this excited state, how much of your Purcell effect goes into light? Because some of it goes into light and some of it goes into heat, into absorption in the cavity, particularly in this type of cavities. So we have to address the emission rate of this emitter in this cavity by calculating the local field, which is the excitation, and then calculating the radiative yield, how much of this emission of these local fields go into the far field. And then here it comes a very seminal paper by Lucas Novotny, almost 10 years ago, where he actually did this calculation, right? Is the emission rate as the product of the excitation rate and the quantum yield. And he put a metallic nanoparticle here and a chromophore here, and he could control the distance, the separation distance of this chromophore. This is the two-level system, close to your metallic particle, your plasmonic resonator, your plasmonic nanoantenna, your plasmonic cavity, and you can see how the two contributions, the excitation rate here as a function of separation distance increases here in red. So the closer you put your emitter to your plasmonic antenna, the more local field you get, and then you increase. But then we have the other part, the blue, which is the quantum yield. And we know that the quantum yield collapses and goes to zero as you get closer to the antenna. This is the fluorescence quenching. If you have an excited state and you put it too close to the metal, it doesn't go to light, it just goes to heating the metal, right? And this is this blue decay. Now, the probability of emission of an emitter close to a plasmonic nanoparticle is the product of these red and blue curves, which is here in black for different radius of the particle. So you can see that when you multiply this and this, you have an enhancement of the emission as you get closer to the metallic nanoantenna, but at some point, which is typically 5 to 10 nanometers, there is this quenching of the emission. So antennas are very good to enhance the emission of light as you get closer to them, but if you get too close, you lose the whole enhancing power, okay? So now we can do this calculation ourselves. We believe Lucas Novotny, but it's always good to do the calculation yourself. You put your tip, which is one type of particle, you put your emitter, which is this zinc tallocyanan, and you calculate these two terms, the excitation rate as a function of tip molecule distance, and you see how this increases. But then you calculate the quantum efficiency, and here you get the quenching. When you make the product, you get quenching with the metal, with the emitter goes very close to the metal. And now the question arises, and many scanning tunneling microscopists came to us some years ago asking, why do we see light coming from molecules in STM cavities? And actually they did. This paper from Shen Xiaodong's group had this zinc tallocyanan in the middle of the plasmonic cavity, and they were seeing very clear light fluorescence emitting from this cavity. And this cavity was about 6 angstroms. And from what we knew, if you get 6 angstroms close to the metal, you should be quenched. There should not be light coming out from there. But indeed, there is light coming from the metallic particle. So actually, this was elucidated not that long ago, just 4 or 5 years ago, when we realized that in a metallic nanocavity, tip on metal substrate, this kind of plasmonic gap or metal insulator metal structure changes completely the radiative yield. So it's not like having a single particle, an open antenna that you get close. You are sandwiched between metal, insulator metal, and then this means that, of course, you have in the excitation rate much larger because you confine better, but more importantly, in the quantum efficiency, rather than quenching, you also have a very good quantum yield to very, very close distances, even below 1 nanometer. Finally, when you get to 2 angstroms, it collapses. But this product now gives you a much better probability of emission in the plasmonic cavity. So the plasmonic cavity is a particularly good antenna. You can get your emitter even to 6 angstroms and still send light out just because it's metal insulator metal. And you localize an antenna better, which has a better radiative yield. And that is known in metal theory, in antenna theory. This is how it works. If you have a single metallic nanoparticle, you just have a typical enhancement of 5, 6 times. The field is spread like that. But if you have a metallic insulator metal, the plasmon gap, excuse me, then you localized light better, but it's not just a question of localizing better. Of course, you have more local field here. It's factor of 60 compared to 6. It's 10 times more. But rather than that, the most important thing is that all this field is very radiative. So this antenna will take almost all the energy of the emitter and put it in photons, whereas this antenna will take most of the energy of the exciton and put it into heat. That's the deal and the secret of plasmonic nanoantennas. So now we know why Shen Xiaodong in China, Guillaume Schul in Strasbourg, they put their zinc tallocyanan separated just to be not touching, and within 6 angstroms, they just see the perfect emission of fluorescence of a single tallocyanan, single molecule emission in a 6 angstroms cavity. Now what we can do is more than that. It's just scanning, using this tip to scan and check the intensity of this fluorescence peak as a function of tip position. And this is an amazing image. It's the fluorescence of a single molecule with sub-nanometric resolution, where you see the structure of the molecule with a hole here of emission, the 4 lobes, and as I say, sub-nanometric resolution. This had not happened only in fluorescence. This has happened before in Raman as well. The group of Shen Xiaodong had done the same, but recording Raman signal from this porphyrin molecule obtaining the different Raman vibrational peaks, selecting the vibrational peaks, and mapping, when they scan these vibrational peaks, and obtaining as well, this was more than 10 years ago, the molecule resolution, subnanometric. At that time, when in theory you try to describe this, it was impossible. There was no way to describe with standard nano-optics this level of resolution. We had to implement artificially a localization of 1 nanometer or sub 1 nanometer of the fields to reproduce in the simulations this level of resolution. At that time, we did it, but we did not know how to explain this level of resolution. This came a little bit later, actually, a few years ago, where we started digging a little bit more into the plasmonic cavity, but not on this mesoscopic description of electromagnetic Maxwell equations. This is the zoom out of the plasmonic cavity. A typical plasmonic cavity has a lateral spread of the field of around 5 to 10 nanometers, even if you have here a 1 nanometer separation distance. That's a typical plasmonic confinement in a cavity. What you can do is to try to dig and zoom in even more. If you zoom in even more, and you go to the atomistic distribution of the plasmonic cavity, which is something that people have not done. People have done this in ab initio community, but not in the nanophotonics community. When you do that, and for that, we had a wonderful collaboration with the group of Daniel Sanchez Portal, who are experts in ab initio calculations of metal and optical response of metals. They calculated for different optical frequencies the fields and the local fields around these metallic atomistic features. And we identify a very interesting thing, which is that on top of the dipolar or, let's say, mesoscopic plasmonic excitations, you have extra localization by atomic protrusions. So atomic protrusions on top of the plasmonic field extra localize the photons to the single atom level. So a photon comes here and parts of the photon remain in a single atom. You can actually do the effective mode volume calculation of these cavities, of these atomic protrusions as a function of separation distance in the cavity. This is separation distance, this is the effective mode volume for different configurations. This is a tip to facet. So this would be the blue one, tip to facet here, tip to facet. We also did facet to facet, tip to tip. But the important message is that for certain separation distance, typical of tunneling, you get around 1 cubic nanometer or smaller. So this allows you to talk about sub-nanocavity, picocavity. So we introduced the concept of picophotonics in the sense that you localize photons at the single atom level. And it's this single atom level that brings the resolution from the 5, 10 nanometers to the angstrom scale, what is the new, not plasmonics, it's subplasmonic probe that allows to obtain the resolution. This is the local field on one of these atomic protrusions. Without the atomic protrusion, you have just the standard lateral extension of the field of 10 nanometers. When you start protruding the atomic protrusion, you localize here. And this is exactly what we do in our tip on molecule experiment. We had in the tip typically these atomic protrusions that extra localize. This is the lateral extension of the fields. In a typical nanocavity, when you use the picocavity, you see that the reduction of the spread is a factor of 10. So here you have your sub-nanometric proof. So now we can understand this resolution, sub-nanometric of the Raman signal, thanks to the picocavity. And now the simulation we did so many years ago, just like that, without knowing what was the source, the physical source of the resolution, now we can explain as single picocavities, atomic protrusions that localize the field. So now we can calculate it, and actually I can show you in 1 minute how to reproduce this. We wanted to do, as I said, this coupling strength calculation, local field acting on the point dipole, but now, instead of having a standard nanocavity with a standard homogeneous field acting on a point dipole, what we have is a picocavity acting on a spread thalocyanine, which has an electron density of excitations very spread. So we have to actually incorporate the stream inhomogeneity of the picocavity and also the stream spread of the transition, of the electronic transition density. So now we don't have a point dipole anymore. This would be the dipolar transition. You see here positive, negative, and then we have this distribution. So now, rather than acting with a single local field on a point dipole, we need to change this calculation of the coupling strength as an integral in the whole volume of the transition density with the picocavity field. So it's a convolution of both in the whole volume. And when you do that, and you calculate that, and you scan it as a function of the picocavity position, you can obtain the coupling map, which reproduces perfectly the resolution features of the experiment, the black hole in the middle, the four-lobe thing, with subnanometric resolution. So you need really the picocavity resolution and the electronic density, transition density, spread in time to really reproduce and understand the experiment. More things that we have done lately, not only focusing in the intensity, and I think I have like 3 minutes left, but very interesting with Guillaume Schul, we have not paid attention only to the intensity of the emission, but also to other features like the broadening, the Purcell factor, and the energy shift, what we call the lamp shift, which are connected for a point dipole with the Green's function of that point dipole. The imaginary part is the Purcell effect. The real part of this Green function, an emitter in a cavity, is the lamp shift. Now we can do the same thing that as we do in cavity QED fashion in a nano-plasmonic cavity fashion with the two-level system, the cavity, and try to calculate both the real part of this Green's function and the imaginary part in this extremely non-homogeneous cavity with this extended transition. And that's what we did for this molecule with Guillaume. It's a free-base phthalocyanine. There is no zinc here. They have two tautomers, so these two hydrogens dance. And actually, when you check the experimental light emission, you can distinguish both directions of the hydrogens because of the addition to the surface. So they break degeneracy. You can filter one and the other and obtain intensity maps. But the most important thing, an interesting thing, in this cavity QED fashion is that they can retract the tip, that is, increase the coupling, or increase the coupling, and then you can see the shift, which is the lamp shift, and the broadening, which is the Purcell factor, because you are controlling the local field of the cavity by retracting. So they are able to map, they put themselves in one of the positions, they can scan and obtain the experimental peak width, that will be the Purcell factor, and also the experimental peak shift, which will be the lamp shift. So what we just need to do is the same that we did for the intensity, this integral on the whole volume of the cavity, of the picocavity field, and the electronic distribution of the two-level system transition. We do the same, but now for the real part and for the imaginary part to calculate lamp shift and Purcell fit. When you do this integral, you obtain a perfect description of the Purcell factor distributed, what matches perfectly. This is experiment, this is our theory, and the same for the experimental peak shift. The Purcell factor resolve, intramolecularly resolve. Okay. With this, I think I have run out of my time. I just wanted to say a last word about how you can use this kind of picocavity concept, reducing the effective mole volume to the limit, one single atom, to improve and boost other processes, which are not picocavity exciton, but maybe picocavity vibration. So we have done exactly the same. We have done exactly the same using a picocavity, but in another context, not in a scanning probe microscopies, but in this kind of nanoparticle on a mirror cavity, this wet, dirty chemistry, to improve and to get non-linearities of Raman signal. So let me go very quickly to the last. I'm going to skip this of molecular optomechanics. I knew I wouldn't have time for this. This is the kind of situation. This is the kind of situation, the particle on a mirror. And then within this facet of the particle on a mirror, you have here your self-assembly monolayer. And when you illuminate, once in a while, these atoms pop up and produce these picocavity features. Let me show you how it works. You illuminate, and some of the atoms, this is a molecular dynamic simulation, and this is the picocavity creation. And this happens all the time in Raman spectra. For instance, here, as a function of time, the group of Jeremy Baumberg here record the Raman spectrum, the vibrational spectrum of these self-assembles on this nanocavity. And at some point, these new lines emerge. These new lines are activated by the creation of a picocavity. And we can understand that from in many ways. We can actually calculate the atomic scale hotspot, how it induces new Raman lines, they coordinate with everything. And when you calculate actually the Raman signal of these new pico cavities, let me show you the final result. They can map as a function of laser power the anti-Stokes, which presents a very non-linear, very quadratic, non-linear optomechanical interaction of a few molecules around the pico cavity. This kind of behavior, which departs from linear, is only possible to the extreme reduction of the volume of the pico cavity. In a standard nanocavity, you would not get this. What we are doing in this context we are studying all this. Resonant SERs now to produce a hybrid optomechanical model. We are also checking collective effects, which are a result of the cross-talking of one vibration with another, creating collective vibrational effects. This we do with Ruben, Esteban, and Adrian in my group. We have actually checked also the optical spring effect, which is in optomechanics, the analog to the lamp shift. And also, very importantly, two color correlations. This we have done with Alejandro González Tudela, describing the statistics and the coincidence of the two photon correlations in these optomechanical features. So this I just showed you to see that on top of the single signal, there's a lot of things to engineer states with this optomechanical and excitonics interaction. And with this, I think I've run out of my 40 minutes, and I just wanted to thank you for your attention.
Thanks. So, Javi, very nice talk. I have two questions. You didn't talk about polarization of the field in this plasmonic cavity, so I was wondering whether it's still well defined and whether you have sort of selection rules, maybe spin-dependent transitions of these molecules. And second, what's the prospect of engineering these pico cavities? So, do they appear at random, or can you engineer them deterministically?
Thank you. Yes, these are two good, important points, right? So I didn't mention it, but in these cavities, typically the field inducing these pico cavities is like this, typically, right? This is like a lightning rod effect, almost, so it goes like this. Now, if you remember, this coupling strength is the scalar product of the local field and the dipole moment. If you put your molecule here, standing like that, with the dipolar moment like this, the scalar product of this field, which is like this, with the dipole moment, which is like that, is 0. That's why we have weak coupling regime. Obviously, it would be very interesting to engineer the polarization of these pico fields to try to align better with the dipole of the emission. Maybe you could reach a strong coupling in a single emitter, for instance, right? Or you can do something else, which is something that our student Javier Aizpurua is doing, trying to put the molecule standing up and aligning the dipole with the local field and see the spectrum, if you can start seeing a splitting or not. So that's regarding polarization. There's a lot of things that you can do. And regarding your second point about engineering the pico cavities, of course, this would be the dream of spectroscopies, right? But to be honest, this is very hardly controllable at this point. In room temperature, you illuminate and they pop up for a few seconds, they disappear, they appear somewhere else. It's a little bit more control in the STM, where you have very low temperature control, but you don't know exactly how is your pico cavity, okay? So there's a lot to do in this. It's not nanoscale, it's sub-nanoscale, really. Now, there's no control yet.
Thank you very much for the nice talk. It's been pretty educative. I want to ask about the operating the STM, because I was just thinking that you have destroyed like many tips before you achieved any kind of result. So you were also talking about the atomic protrusions that make the cavity.
Yeah.
Those are made, or those are just found in every tip in like a little bit randomly? I don't know. Can you a little bit explain?
Yeah. So actually, for me, it's very easy because we are theoreticians, right? So all I have to say is well, yes, I have this cavity. You saw how I just put the boundary like that with the form of the Pico cavity, and then put like that, put the standard thing, I calculate, and it's like that. But to achieve experimentally, which is what you say, this, and we collaborate with this, with the best, to be honest, with the best STM-induced fluorescence groups in the world, Shen Chaodong in China, Guillaume, I'm sorry, there might be other groups that do very good, but these were the pioneers, right? And you see here, this is a control experiment. Emission when the laser, when the tip is retracted. Emission when the tip is in, but you have it directly on the silver without the separator. When you only have the separator, when you have this, when you have that. So this only works after a bunch of recipes that took them decades to get. So you're right, it's not come and get the light, but once you get the recipe, and Shen Chaodong got this recipe like 10 years ago, for instance, the sodium chloride thing. If you don't put the sodium chloride separator, you don't get any light out, any. And for many years, people don't get any light. You put one monolayer, it doesn't come out. 2 monolayers, it doesn't come out. With 3 monolayers of sodium chloride, boom, it just comes out. Until you get to that, it takes 2 decades of development. But once you know it, now everybody's using that, and everybody just put the tip and get the light. It's quite a standard. It was not a standard, now it's a standard. It's not so tricky to get light now that you use the recipe that they have established.
Hi, first of all, thank you for your talk. So I was wondering, when you were modeling the interaction that was going on in a cavity, and then you treat your emitter as a 2-level system, as usually done with the quantum dot. I was wondering if maybe you have considered, or you have done already, like some sort of like modeling of more complex molecules or systems where the 2-level system is no longer accurate for what is going on.
Yes, absolutely. So this is just a 2-level system, as I said, a single molecule. These phthalocyanines work as 2-level system, but we have done work with quantum dots, for instance. And in quantum dots, we see that they are not just a simple 2-level system, they have dark states. These dark states couple differently. So we have adopted, to describe this, a methodology completely different to this classical coupling of fields on dipoles or electronic transitions. You go to cavity QED, you put your system rates, you solve the master equation, and then you see really very strange things when the strong coupling is not a standard, it gets into 3 peaks. So answering short to your question, there are much more complex dynamics of excited states coupled to plasmonic fields. And if that's the case, like in quantum dots or in molecules which involve 3 levels, and the case of triplets, singlets, and so on, you need to sophisticate either the quantum chemistry of your molecule or the decay of levels in cavity QED for quantum dots, for instance. So you have to do that. That's another talk.
Okay.
Thank you.